Hello students, in the last video we were talking about the polarizer and analyzer. Polarizer is the one which polarizes the light and analyzer is the one which check whether the light is polarized or not. So I told you when the analyzer is kept perpendicular to the polarizer, no light will pass through the analyzer, the intensity is 0. That is what we did in the last video, the last diagram. There is a law governing that. That law is called Malus Law. That is what we are going to discuss now. Malus Law tells that when a beam of polarized light is incident on the analyzer, the intensity of the transmitted light through the analyzer is directly proportional to the square of cosine of the angle between polarizer and analyzer. That means intensity of the light passing through the analyzer, that is directly proportional to cos square theta, where theta is the angle between polarizer and analyzer. So I will be writing like this: I proportional to cos square theta. You can see the angle which they are marked. This is polarizer, that is the analyzer, angle between them is theta. So I proportional to cos square theta, then I can write, to remove the proportionality sign, I can just directly write like this: I is equal to I0 cos square theta. Here you can see the vector is resolved as a cos theta and a sin theta. So I is equal to k a cos theta whole square. Now why I am taking a cos theta? Because a is the amplitude of the electric vector transmitted by the polarizer. Then only the component a cos theta will be transmitted by the analyzer. A cos theta is actually the parallel component. A sin theta is the perpendicular component which cannot be transmitted by the analyzer. So only a cos theta will pass through the analyzer. That is why we are taking only the cos component of the vibration. So when I square it, I is equal to k a square cos square theta, and a square is I0, or in some textbooks it will be written as Im, maximum intensity, or I0, maximum intensity. Okay, so Malus law, final equation, I is equal to I0 cos square phi by 2. Okay, now just see the different cases when theta is equal to 0 or 180 degree. Cos 0 is 1, cos 180 is also 1. At that time the intensity is maximum, I is equal to I0. Now when theta is equal to 90 degree, cos 90 is 0, therefore intensity is equal to 0. Okay. So don't think it will come I0 always. I can take polarizer 1, polarizer 2, polarizer 3, like that. So when I take polarizer 1 and 2, the intensity between them is considered as I0. So always it won't be I0. For example, what I mean is, as per Malus law, we can just say like this: suppose here there is a polarizer, here there is a polarizer, here there is another polarizer, here there is another polarizer. There are three things. And let I0, I am not drawing the vibrations, I am just putting the arrows showing the wave. Okay, let this be I0. This polarizer and analyzer are having the angle 30 degree. This polarizer and analyzer are having the angle 60 degree. Imagine like this. Now when when the intensity I0 passes through the first polarizer, passes through P1, the intensity which is coming through this will be reduced to half, I0 by 2. Now, this light is passing through the second polarizer. So, I am first writing intensity I1. Intensity I1 is I0 by 2. Now, I am finding intensity I2. I2 is the intensity which is passing through the second one, this one. When I consider I2, I will take intensity of this one and theta between these two. Okay, when I consider I2, I will take intensity of this and the angle between these two polarizers. That is how we apply Malus law, and Malus law equation is I0 is equal to Im cos square theta. So, I2 is equal to, here the intensity is I0 by 2. So, I will write I0 by 2 cos square 30, and cos 30 is what? Root 3 by 2. Cos square 30 is 3 by 4. So, I0 by 2 into 3 by 4. You will get the answer as 3 by 8 I0. So, here the answer will be 3 by 8 I0. Now, the light is coming through the third polarizer, that is P3. When I consider the light passing through the third polarizer, I will take this as the intensity and this as the angle between these two, P2 and P3 as the angle, that is 60 degree. And just see, I3 is equal to I3 is equal to 3 by 8 I0 cos square 60. So, 3 by 8 I0 cos square, cos 60 is 1 by 2, cos square 60 is 1 by 4. So, 8 4s are 32. So, 3 by 32 I0. Therefore, the intensity here we are getting as I3 is equal to 3 by 32 I0. This is how we have to apply. This is how we have to apply the Malus law to find the intensity. Okay. So, you can please take down. The question will come like this. They will give P1 and P3, both of them are perpendicular. You can see total angle between P1 and P3 90 degree. So, they will ask a question, P1 and P3 are kept perpendicular and a second Polaroid is kept between P1 and P3 whose angle is 30 degree with respect to the first one. So, if this and this makes an angle 30 degree, obviously this will make an angle 60 degree because P1 and P3 are perpendicular. That like that only question can come. So, first they give two crossed Polaroids, two perpendicular Polaroids, crossed Polaroids. Then a third Polaroid is kept in between and they will give an angle like this, and by using Malus law you will be able to find the intensity in this format. Okay. Now, when the unpolarized light is incident on the analyzer, the intensity of the transmitted light is 1/2 of the intensity of light. That is why we take I became I0 like that. Now, when will the emergent light will be half of the intensity? Through the analyzer. When the light is passing through the analyzer, when can intensity be half of that? When the analyzer and polarizer is kept at an angle 45 degree. Because when both of them are at an angle 45 degree, cos square 45. Cos 45 is 1 by root 2, cos square 45 is 1 by 2. So, if I0 is the intensity of the light coming from the first polarizer. Then I0 by 2 will be the light which is coming out through the analyzer. Okay, that is when both of them are at an angle 45 degree. Now comes polarization by reflection. When a ray of light, when an unpolarized light strikes here, light will partially get refracted and partially gets reflected. Imagine the light is coming from air and striking a water surface. So partially it will get reflected and partially it will get refracted. The refracted light will be always partially polarized. We cannot polarize it completely. But the reflected light can be polarized. When the incident light, when the light is incident at an angle equal to the Brewster's angle or polarizing angle, at that time the reflected light will be completely polarized, having vibrations perpendicular to the plane. That is why I have only put the dotted lines. Vibrations are perpendicular to the plane. Okay. So for every other angles the light will be unpolarized. Only at an angle called polarizing angle or Brewster's angle, that angle of incidence. At that time the reflected light will be completely polarized, having vibrations perpendicular to the plane. That is polarization by reflection. The intensity of the transmitted light through the medium is greater than that of the plane polarized reflected light. That means this intensity is more than this intensity. Now I want to tell you one more thing. Whenever this polarization happens, always when that polarization happens, always the reflected ray and the refracted ray, they are perpendicular to each other. The reflected ray and refracted ray are perpendicular to each other. That is why I have marked the angle 90 degree. Now listen, from that figure, theta p plus r is equal to 90 degree. R is the angle of refraction. If this is theta p, I can mark this also as theta p. This is also theta p. Why? Angle of incidence equal to angle of reflection. That is why. This is 180 degree. So theta p plus 90 plus r is equal to 180 degree. So theta p plus r is equal to 90 degree. Okay? Or r is equal to 90 minus theta p. Now refractive index mu. Refractive index mu can be written as sin theta p by sin r. We are writing mu b a. You can just write, we usually represent n. So instead of mu, it is better to write n. N b a. Refractive index of medium B, that means water, with respect to the first medium. That is why I write like this, NBA is equal to sin theta p by sin r. Instead of sin r, I can put 90 minus theta p. And what is sin 90 minus theta p? Cos theta p. So I will be writing sin theta p by cos theta p, the polarizing angle. And what is sin by cos? Tan. So NBA is equal to tan theta p. Or in general you can write refractive index, N is equal to tan theta p. This law is called Brewster's law. That means refractive index of the medium is equal to the tangent of the polarizing angle. That is called Brewster's law. Okay. So please take down. Now the last thing is Polaroids. Polaroid is a special sheet of material where the molecules are arranged in a definite pattern. I already told you, in glasses, in spectacles, they use Polaroids. So the electrical vectors which are in the direction of that aligned molecules. I told in Polaroids the molecules are aligned in a definite pattern. So the electric field vectors which are in the direction of that aligned molecules will be absorbed. The perpendicular vibrations will pass through. So the vibrations which are coming out through the Polaroid will be having always vibrations perpendicular to the plane. So the Polaroid can absorb the parallel vibrations. Now you can see uses of Polaroids. Polaroids are used in sunglass, Polaroid filters, laboratories, headlights of automobiles, three-dimensional pictures. To view the 3D movie, they are giving you a glass. That glass is actually Polaroid. Then in our LED TV, the front glass is actually a Polaroid. That is why you can just watch, you can see this TV. I can watch from here. There is no problem with the eyes because the light here is Polaroid. There is a Polaroid sheet here, so the light coming out is polarized light. Therefore, there is no glare. So it is comfortable to the eye. Then we can use that in automobiles to reduce the glare of the light. So all those are the applications, practical applications of Polaroids. And there is one more thing, polarization by scattering. Atmosphere contains lot of molecules, right? Air molecules. So sunlight will, when the sunlight strikes the atmosphere, the electrons of those molecules have vibrations in the parallel and perpendicular directions. So the electrons which are vibrating along the direction of the electric field vector, they cannot transmit energy to the observer. They will absorb. So electrons which are vibrating parallel to the direction of the electric vector component will be absorbed. That electric vector component will be absorbed by the electrons. They cannot, those electrons cannot transmit the light to the observer who are standing on the ground. But only the perpendicular vibrations can be sent by the molecule. So molecule, the parallel vibrations of the electric field will be absorbed by the molecule, and perpendicular vibrations of the electric field will be transmitted to the observer. So what the observer is seeing, observer who is standing on the ground, he will be seeing a polarized light. So that is called polarization by scattering. So the light, that doesn't mean that the sunlight is completely polarized. Sunlight strikes certain molecules, that molecules will scatter the light, and due to that scattering, those lights will be polarized. But there are other lights which are coming from the sun which is not getting scattered, and they will not be polarized. So usually the light what we see here will be partially polarized light. Okay, so those are the three types of polarization. The first one is polarization through a crystal, and there we studied Malus Law. Second one is polarization by reflection, and third one is polarization by scattering. So with this, our topic comes to an end. So that is all about polarization. I hope you have understood the topics. Please take down the notes from both the videos. Okay, thank you.